Welcome to the Learning on Graphs training group.
Where Alexander Tong, who did our introduction here today, will present his paper on conditional flow matching and how to improve it with Minibatch optimal transport, for example.
Sure. Yeah. So I'm a postdoc at Mila. I work with Joshua and many other people now. And I'm very interested in sort of generative models. My sort of particular domain of interest is the single cell trajectories. I'll talk a little bit about that at the end, but you know, it's sort of more general, this sort of approach. So yeah, I think this is sort of this flow matching thing is very useful, and it's fairly simple to understand once you understand the basics. So hopefully I can give you sort of the concepts, and then we can discuss sort of the applications and different aspects of it. There's sort of many different ways to think about it. So yeah, let's dive in. So let's see. Perfect. Okay, so I'm just going to talk a little bit about the background. So you've got talking a lot about diffusion models, but also sort of what these flow models are, and specifically like the older versions of flow models that didn't work as well, and then sort of the improvements to these. And so how do you improve them with this sort of simulation freeze? By that I mean sort of instead of integrating over time during training, you don't integrate over time, just like diffusion models where you can sort of pick a random place and regress. You can also do this with flow models. Then I'm going to talk about how to use optimal transport to learn better flows. So this is sort of my work building on top of the initial flow model work. And so this has sort of applications in how you control the flows. So sort of diffusion models, we learned how to do one type of flow, which is from data to noise, but there's sort of other ways to do flows, and it's useful when you want to do specific types of sort of marginal flows. So just recap, diffusion models, right? You learn, so you have a fixed forward SDEs, you go from data to noise, and conditioned on a data point, you have a specific sort of sample of noise that you go to, right, according to this SDE. And then what you try to do is learn the score function, which can return from the noise back to the data. So this works quite well because since you can simulate the forward, or you can sort of, simulate the forward SDE, right? But you don't have to you can pick a random point from the probability distribution without simulating it, basically. You don't have to sort of forward simulate and backward simulate and differentiate through the whole thing. You can just pick a random point and regress the score function. So this is in contrast to the sort of older continuous normalizing flow work. This is sort of built on normalizing flows, which just went from a Gaussian to some data with an invertible transformation. But this instead uses a continuous transformation. So instead of sort of integrating with an SDE, we use an ODE. So you have this just the sort of flow and no noise. And then the reverse ODE, right, there's no sort of score function correction, right? This GT term is 0. So it simplifies down to be exactly the same thing. It's if you don't need this. So it's just sort of negative F, basically. And so, yeah, you reverse the ODE to get back from the noise to the data. And you can learn a function that does this. However, how do you train this thing? So the sort of the way that it was trained before is you use a neural ODE to represent this invertible transformation. So big F is invertible, and it goes from time 0 to time 1. But it's sort of an integral of this actual parameterized neural network that parameterizes the derivative. And so how do you train this thing? Well, the easiest way is sort of to maximize the log probability. So in particular, we can have a form for the log probability at time 1 if we have the density of that point at time 0, and we look at the sort of integral of the trace of the Jacobian over time. And so this is hard in two ways because you need to sort of find the corresponding points, right? From time 1, you integrate to time 0, and you also need to figure out the sort of the derivative, this trace term, right, which is quite expensive, especially in high dimensions. And so,
are you now?
Yes.
Time 1 for you will now always be the prior distribution.
Yeah, so this is always complicated, right? Because diffusion models use time 0 as the data and time 1 as the prior. And I often use time 0 as the noise distribution and time 1 as the data. So yes, in all my notation, time 1 should be the data, and so you should flow from noise to data. But yes, this is
Okay. Then why
the
did
confusion
we
point.
just say that we
Yes.
have to integrate from time 1 to time 0? Okay, that we have to do if we would want to train with data samples.
Yeah, exactly. Yes. So if I have samples at time 1, then I can sample here to calculate the sort of log probability of all those data samples according to the model, right? Would be sort of the how probable they are to sample, and then integrating over
But
time. Yeah.
we would only know if we have a if we have a model that's invertible, and we could also basically go the other way around. And now, if we don't want these architecture restrictions that we have with the normalizing flows, we can maybe also have just an arbitrary model and only need to integrate forward.
Exactly. Yes. Yes. So this is an almost arbitrary network, right? It needs to be sort of smooth enough, but that's much easier than being fully invertible. So this is, you can put any sort of architecture here, but it does need to be smooth enough, and then you can have a big F that is invertible. Yes.
I feel cheated, man. Like I say something wrong and you say yes. So
it's mostly right, correct? Yes.
no. So the if we train our normalizing or continuous normalizing flows, they do not, like, the architectures do not have to be invertible.
Yes, sort of, right? Like the network that you parameterize is not invertible, but of course the whole thing, if you did the integration, is invertible. So if you picture the if you think about it as the rolled out piece, right, it is invertible. That's the trick, right?
Okay. Okay, then can you go a slide back?
Yeah.
So what did I want to ask here? Right. So in our diffusion models, we're only learning the score and F is predefined. And now in your ODE, you're putting both things together.
Yes.
Right? So you're learning
Correct.
both at the same time, so to say.
Yeah, so this is actually so this is the same basically. So this F these are equivalent Fs, right? You sort of do forward and reverse are the same, right? So if you took the noise to 0, right, then this equation would just this part would go away, and then if you put this to 0, right, this part would also go away, and this part. So you would have this sort of same equation. Of course, this would not be very helpful because you would say, okay, to go forward, I have this F, and to go reverse, right, I have this F also, but that would give you from the same noise point to the same data point, and sort of this is not very helpful, right? Like, you haven't learned anything basically, right?
But in our diffusion model, we just have our predefined F, and that just something that goes to makes the mean go to 0 or something like that, right?
Yes, or exactly, or nothing at all. Yes, so you could, right, like just move the mean, but you would need to condition on where you're going basically, right? So it's you need to sort of learn this score. Yes.
Yeah, so if we were now to, like, can you go a slide forward? Like here it seems, why don't you put a theta at the F, so to say? Because otherwise it makes no sense to diffusion model person.
Yes, that's fair. Yes, I agree. There should be a theta probably, right, in this, in this thing, and a theta in here. Yes, I agree.
I mean, okay. Well then, let's
yes.
just making sure I'm understanding of all the things perfectly, and then let's go.
Perfect. Cool. Okay. Yes. Yeah. So this is very painful, and we don't want to do this. And the whole goal of this sort of flow matching thing is not to do this and to do a different loss of training. So everything else stays the same, right? So inference requires this integration, similar to diffusion models, right? So it's sort of making training. You're training it's sort of like training layer by layer instead of right, the whole model at once, right? So I think of diffusion models. You could train using forward and backwards through this entire SDE, but that's very painful. So we do this smarter thing, right, where we train layer by layer for this very specific flow. Similar thing, you know, we train the old way was right to train this whole thing end to end. This could give you very flexible flows, but it's not very easy to train, just bad gradients. And so yeah, getting rid of this and moving to something better is the goal, right? So yeah, this we just sample that noise, but of course it's a sort of harder inference because it uses the stochastic differential equation. So although there's sort of ways to correct this, the stochastic differential equation just is inherently harder than solving ODEs, right? So this continuous normalizing flow, you only need to solve the ODE instead of the SD. Of course, it's been hard to train. Of course, there's sort of this probability flow ODE literature, right? And so you can convert these diffusion models to continuous normalizing flows by sort of using this special formula, right, that says the ODE has the same marginal flow as the SD if you use this correction term. So, you know, there's sort of a link from diffusion models to continuous normalizing flows, but this is sort of for a very specific flow. So actually, you know, you can train these probability flow ODEs using either the diffusion model loss, or you could train it using the CNF loss, but you don't really want to train it with the CNF loss for now. Cool. Yeah, so these are very different looking. However, basically the idea is to turn the CNF loss into something much easier. It looks very similar to the diffusion model loss, and also this is just preview, but that's where we're going. Cool. Okay. So the main idea is the same as diffusion models in that you can train against a conditional flow, which is equivalent to regressing against the marginal flow, right? So diffusion model is a conditional flow, is given a data point, I know how to go towards noise. It's just right adding Gaussian noise and maybe subtracting the mean. But I don't know how to go from noise to data, right? Or from data to noise, basically, right? So I need this sort of equivalence by, if I can do this conditional matching, then the marginal will also match. That's the whole trick. So just notation, PT is going to be the flow. So that's the sort of density over time. UT is going to be sort of the, we were using F before, but UT is sort of the marginal flow in this literature. So UT is a vector field that changes over time, and that is sort of, we call it generates PT if given sort of P0 and UT, and you integrate UT over time, then you get PT, if that makes sense, right? So, starting at these samples of 8 Gaussians, if you integrate each sample according to UT, according to flow, then the probability flow will be this PT, right? So that's what it means for a field to sort of generate a probability distribution over time. And so if this flow has this very specific form, which if you stare closely, it sort of looks like Bayes' rule for right, like if I looked at these as probability distributions, it kind of is very interesting. It has sort of this marginalization over Q. And it turns out that this works essentially so that if you regress against the conditional flow, it's equivalent to regressing against the sort of marginal flow, right? So this is UT, that's very hard to know. So this is the marginal flow, and UT of X given Z. So some condition is sort of the conditional flow. Okay. Yeah. Yes. So this is the.
Let me first ask the person to stop drawing, and second, how many flows do we have? No, how many vector fields do we have for each flow?
How many vector fields we have for each flow? Sorry, what do you mean by which vector field are you talking about?
How many U of T's are there for each P of T? Like, is the mapping 1-to-1?
Gotcha. Yes. So the mapping is many flows can go to a single probability distribution. Yeah.
This is just like some curl that we can add to the flow, or?
Yes, basically, yes. So curl is sort of, curl would work if the the probability distribution was uniform, but sort of any flow where the divergence doesn't change. So you can sort of, right, like rotate, for instance, for Gaussian, you could rotate it and it would be fine, right? Any rotational flow is fine. Curl, but curl is sort of fine. You need a sort of correction term for the density. So if you sort of do curl corrected the density, then any flow is fine.
If I, for example, have a Gaussian, then if I have my vector field that gives rise to this Gaussian that maybe also evolves a little bit over time and the standard deviation changes or something. And if the vector field additionally to pushing in the mass and making the Gaussian smaller or something, if it additionally rotates the mass, then nothing changes in terms of the density.
Yeah, the density is totally fine, exactly. Yeah.
Then let's see what the chat is saying. The step size, I thought, Hannes. Okay, no, nothing in the chat. Then let's see what else do I want to ask? Good, we have our vector field, and the vector field gives rise to a flow, which is this evolving probability distribution. But now you're saying for training, or no, you're saying regressing against for training, right? We could sample P of Tx and then put it into our U of Tx and then regress against U of Tx. But yes, well, we can't really. So what you want to do now instead is sample P of Tx given some z and then put that x into our U of T of x given some z and then just average over all these choices of z, yes, which exactly, is sample from your Q of z. And then you say you end up with the same thing as we had done what we can't do.
Yes. Yes.
Okay, then what is Q of z? What is P of x given z?
Yes, these are excellent questions. So it can be many different things. And this is basically the biggest difference between all the flow matching papers, right? They all choose sort of different choices for P of T of x given z, what is z, and sort of what is the flow, right? Like, so they're all slightly different, but very similar. So I guess I'll just flip forward to this table. Basically, you can choose Q of z to be many things. So the original flow matching paper, for instance, just chose Q of z to be data, and as going back to Gaussian. So this mu t of z, so is sort of the we need to talk about this a little more. But basically, right, like you need you can choose many different things for Q of z depending on what you're trying to do, and this will give you different properties. So yeah, but yeah, I guess I'll explain these sort of flow matching first, and then sort of how you get to independent and optimal transport. And so we'll just get an understanding of the different sort of choices of QZ and what they give you.
I love this table. That's why I like your paper a lot.
Tables are, yes, useful for understanding some of these things. I think I like them too. Okay, so yeah, so there were three sort of original flow matching papers. This was one of the three. So this one is going from Gaussians to data, specifically for image generation and very high quality image generation, which is why it's quite interesting. And so this is out of Meta. And so they had sort of results that were comparable, possibly better than some of the diffusion models, although sort of hard to tell, right? Like I think sort of the number of function evaluations is better, but of course these are sort of not the top, best diffusion models out there. They're sort of pretty good, basically, right? So it's not there could be more tricks to implement, basically, that improve both models, but at least it says they're not out of the range of diffusion models for sure. And yes, let's see. Okay, so how does this work? That's also known as rectified flows and stochastic interpolants, other names for flow matching. These were invented sort of at the same time by different groups. Okay, so here's how this works. So, okay, here's Q of x1. So this is considered data. Q of x0 is a normal distribution. And what is our conditional flow? Well, our conditional flow is going to be this, right? PT of x given a data point. So Z is a sort of data point here, data point 1, data point 2, data point 3 in red, green, and blue. And how it's going to work is that PT of x given z is going to be a Gaussian. That's a small Gaussian around the data point and is a normal 0, 1 at time 0, right? So you're going to interpolate the Gaussian sort of between this small one and this large one. And sort of this is the conditional flow.
Okay.
Yeah. And so the marginal flow, right, is just the sum of all these Gaussians. Very easy. And these Gaussians are very nice because there's sort of this closed form. So there's many choices, right, as we were saying, of UTs that generate these PTs, right? So many sort of UTs that can generate a Gaussian over time, but this is sort of the simplest one in some sense. So this is the optimal transport one. So this is derived from the formula of optimal transport between Gaussians. So this is a 1D sort of formula, but you can extend it to any dimension. So the sort of, yes, optimal transport is sort of curl free, right? Like there's no rotation. So it's sort of the simplest one, although you can use any. It's probably best to use this one, I would say. Yes, so here we can derive a closed form for this UT of x given z for this sort of Gaussian that shrinks over time from right normal 0, 1 to the data, and then regress against it. So right, the procedure is going to be I predict my data point, I pick a data point, I pick a random place in time, and then I know sort of I can sample from the Gaussian, right, of PT of x given some data point, and then directly regress against UT of x given z. So yeah, feels very similar to diffusion models, right? So this is one particular path, but actually what they explored was sort of with diffusion. So they have two models. One is with this OT conditioning, and the other is with diffusion path. So diffusion, right, you would sort of subtract the mean, and the standard deviation, right, would sort of grow with this with schedule. So it wouldn't be exactly this path, right, but it would be a growing Gaussian to normal 0, 1. So it's interesting that you can do sort of flow matching with the same probability paths. So you would get the same marginal over time as diffusion models, but just regressing the flow instead of the score.
Yeah. So how does the conditional path look different from like you say the difference between this diffusion model, conditional flow path, and the OT optimal flow, the OT conditional flow, is that there is this OT quantity or this OT addition or guarantee that we have for transporting, for example, a Gaussian, and then it's having curl-free transports of it. And yeah, like, can you explain a little more? Why is it a problem to have the diffusion path instead, and so on?
Yeah, I think intuitively, for right, like this was their example basically. So it's sort of hard to see in the conditional case, but right, like if I was only going to one point and I want to integrate from like the Gaussian to this one point, right? These are the paths that would take me in the diffusion model, right? So right, like, okay, pretend my data set is just one point. It's right here. And this is the Gaussian that is sort of normal 0, 1, right? And then I want to say, here's sort of the paths that I take to get back to this data, right? And this is sort of the flow, right? So you're trying to learn this flow, this conditional flow versus an OT flow. That's like
Oh,
this,
wait
right?
a second. So the blue thingy is our prior.
Yes, exactly. The blue sort of, yes,
And
shaded region is the prior, and this is the
then
data
this
point.
is the Z.
Yes.
That was okay. Why is this now happening? Right, this is happening because with our no. This is not okay. I wanted to say this is happening because we are making random movements in the, yeah, no. Can you, instead of me trying to come up with a wrong explanation, maybe you just say the correct one? Like, why is this happening? Can you give some?
Why is this curving out and then in? If that makes sense. Yeah, it's because, right, it's sort of the schedule, right? So going back to this table, right, this is right, variance preserving. So you subtract the mean basically, right, over time, and then you use this sort of exploding, standard deviation that changes over time, right? So there's sort of this grows fast, right? Basically, so you get a wider Gaussian, and then but you're also moving towards the mean. So you're sort of, visually, right? Like the Gaussian gets wider, and it also moves towards zero, right? But it's sort of, it gets wider quite fast at the beginning, basically. So that's why it sort of happens here, right? Yes,
Okay, so these lines on the right side, they aren't straight.
yes, exactly.
Okay, they look very straight, but
Sorry, this right-hand side? No, these are straight.
what?
These are not straight.
Well, but I mean, here we also have a Gaussian that is increased.
Yes, right. Yes, but we're picking this Gaussian specifically so that it follows this, right? So that the mean is sort of yeah, I don't know. It's this very specific Gaussian, right? Like you could pick any standard deviation schedule, right? But if you pick specifically, right, this one, so the mean goes with t of x. So if alpha is sort of t, and your standard deviation is exactly this one right here, then you get the optimal transport, right? So you could if you change this for this, then you would get this sort of straight line. Yeah. So
Okay.
I guess diffusion models, right, with a very specific Gaussian schedule, right, with T and this, then you would get these sort of optimal transport paths, basically. Yeah.
Nice. Okay, good.
Yeah.
Well then, but there's also one sort of difference between our conditional, like if you go to your flow versus CFM comparison with your numbers, where you show the table with the numbers of performance.
Numbers of performance.
I mean, you
Yes.
yeah, thank you very much. And there we have our FM with the diffusion path, and we have FM with the OT path. But FM with the diffusion path still isn't exactly how we train our diffusion model, right? Because in our diffusion model we only predict the score and we don't predict the F.
Yes.
So we're learning something extra. Is there something to be said about this learning something extra? Do you think this is useful to learn this something extra because it's easier to make this prediction, or do you think it's you have to learn something extra and that's harder? Or
Yeah, it's a good question. I think it's not that different, right? Like, so the difference between them is f, right? Is this f, right? And this f is either like 0 or like 1 minus x, right? So these are very, very simple functions basically. So I'm not too worried about it. Yeah.
Okay, so now Pierre-André Noël says there is no extra. Diffusion learns the backward map, OT learns a single reversible map. So did we fall into the trap again that I say something wrong and you say correct? Or do you agree with me and disagree with Pierre? Or what's the deal?
I think what you meant by extra, right, was this f term. Yeah, so yeah, I think this f term is extra, but it's not, right? It's not that different basically, right? So you're just learning a shift, but it's yeah.
Okay, good. Then what do you think of this? Yeah, let me quickly share my screen. Yeah, right. This plot here, right?
Mm-hmm.
So we have the diffusion path versus the OT path, where we're here at T0 we have our prior, and at T1 we have our the vector field, I guess, of our conditional path, right? And what are they visualizing with this plot or with these plots, or how do you, what should these plots say, right? Because here we sort of have the mean moving, and here the mean on the right with the OT path, the mean always stays at the
So this is right an interesting observation that basically the objective that you're trying to match changes over time with diffusion, right? But is actually quite static with the OT, right? So it's sort of very it's so I don't know. It's could be easier, right? It's argued that it's easier, but I think we don't have so much, right? Like it depends on your parameterization, for instance, right? Like if you're sort of if time is easy to, right? Like these diffusion models work much better if you do this time embedding thing versus like just feeding in time as a parameter, for instance, right? Because you need to vary a lot with time, and so these flow models you don't need to vary as much with time. So, but you still need to vary, right? Like this is not fixed in time, but it's sort of centered around the same place. So it could be maybe easier, right? Like the magnitude is changing over time, but not the sort of direction as much. So maybe it's easier. I don't know.
But is this because so I thought when I looked at this first, this is because here we're only looking at the score function, and here we're looking at the conditional vector field. And in the diffusion model, we only have to learn. We're only learning the score function, this S, and here we're learning the conditional vector field. And yeah, this sounded very intuitive to me, that we have less, as you say, for example, time dependence in this plot here, that then it should be much easier to learn the conditional vector field and then to learn the score function.
Yeah, I think, I mean, it's hard to say, right? Like, is this, like we don't really know the neural networks, right? What they're doing. I mean, this is just the mean moving over time. So like maybe you just, right, like it's just a shift. So if you subtract this mean, right, in the biases at the first step, then it's actually all the same, right? So I think it's maybe easier, right? But I have to be, convinced empirically, right? Because right, like this sort of plot looks different because the mean is moving, right? But a mean, right, is easy to sort of subtract in a neural network. So yeah.
Okay, then I won't be so convinced about this anymore. Can you share your screen again, and let's continue.
Yes, of course.
Very good, very good.
I cannot share while you're sharing, so.
What? Okay.
Right. Okay. Excellent. Working?
Yep.
Perfect. Okay. So we were here. Okay, so we have this nice closed form, and we have this right marginalization that gives us the UT, and so this is great. And so yeah, we can use this and learn it, and now we can do other things, right? So this is sort of the original way of doing it with just conditioning on data points, but you could also condition on the source distribution, and you can also condition on an OT map. So this is sort of the this is the part we add, and there's sort of other works that also do this sort of just flow matching from a source to a target, although they have sort of slightly different theory and slightly different parameterizations. It's very similar.
Okay.
Yeah, so just
okay. Never mind.
Perfect. Sounds good. Yes. So just right algorithmically, this sort of simplest way to do it. So we call it independent conditional flow matching now in the paper, but it's similar to sort of a zero rectified flow or a stochastic interpolant with a specific schedule. Yeah, so many different ways of talking about it, but the basic idea, right, is you sample from both time zero and time one, select random t's for each thing, calculate the mean of the Gaussian, add a little noise if you want, and then regress against the target vector field, which in this case, because the Gaussian is the same standard deviation over time, it's just x1 minus x0. And you do this forever or until you're done. And then you get these nice flows, sort of the conditional flows are these small tubes, maybe tubes of what the zero is often considered, right? It seems to work pretty well. But you don't know what the sort of marginal flow is going to be between these two distributions, but you do know the conditional ones are OT. Cool. And so sort of the simple thing that we've been working on, right, is instead of just sampling from both of these and constructing the paths, sort of do a resampling steps. You calculate an OT map between the two, between the time zero and time one, which we call pi. And so this is a matrix, right? That's, well, it's basically a permutation, which then you can resample from. So now you just have permuted one side. And so now you have these, sort of unpermuted things, right? So you may have crossings here, but you always get these sort of shortest paths in terms of some OT cost. And then you sort of have these flows that are, it's so you have, the same guarantees in that you have this distribution times 0, this distribution time 1, but you sort of change the marginals and change the flows between the two. Yeah. Cool.
Then maybe why would I do the conditional flow matching, or like the two-side joint conditional flow matching? Like, what is the advantage of this?
Yeah, so this works. So yes, I see. So if you're always studying from a Gaussian, I think it's not very relevant, right? This one seems to always work slightly worse. I don't know. We'll see. I guess this one works pretty well because the conditional paths are straighter in some sense. It's easier to sort of do integration. So one of the links, right, is like if the paths are perfectly straight and non-overlapping, then you can integrate in one step, right? So the optimal transport map is integratable in one step if it's the true OT map, because all these paths are straight and they're all non-overlapping. So the vector field is always going to, so the marginal vector field is going to be equal to the conditional vector field at every point, right? Which is quite interesting. And so sort of you'll start here, right? And if you know your sort of conditional vector field where it's supposed to go, then if you just do one step, then you should get your true distribution. Of course, this is very hard because you would need to know the true OT map to sort of do this, right? We're using the Minibatch approximation. But if you have the true OT map, so you do in sort of small data cases, right, then you would get integration in one step. So sort of straight paths are very useful because you can get fewer steps of integration, right, with less error, basically.
Mm-hmm. And then like this loss is kind of unintuitive to me. Like if we just look at this, right? So the x that we have is somewhere in the middle, sampled from our conditional flow. And we tell our vector field the t as well. But then why should it always be x1 minus x0? And kind of why would I always, like, wouldn't I then always tell my model you have to overshoot? Do you know what I mean?
Yes, because so you're thinking like near the end it should be going slower, basically, right? So right, you could choose to go slower, but of course like this if this Gaussian moves at constant speed, then the velocity never changes, right? So just thinking about just the single sort of path, then the velocity here should be constant and it should be going, from at speed 1 from time 0 to time 1, right? So that's the
Okay, good. Thank you. That was a weird thought. Okay,
of course.
Let's continue.
Cool. Okay, so back to this table finally. So many different choices, right? So the sort of there's quite interesting sort of flow matching, right? This one works. So it has conditional OT, right? In that each Gaussian is sort of OT. You choose the OT path between. You choose the OT flow between Gaussians, right? And there's sort of variance preserving, which is a different method, but basically this is kind of interesting. If your data is normalized to have mean 0 and standard deviation 1, then at all time points, PT, so the marginal distribution, will also have mean 0 and standard deviation 1, kind of fun. And then, right, this sort of independent path. So this I just talked about, but you do this sort of straight line interpolation between the two. You get conditional OT, and you can go from general sources, but of course you don't get marginal OT. But if you have the true optimal transport matrix, so the static one, and you did the same procedure, then you would get also marginal OT. And then Schrödinger bridges, I don't think we'll have time to talk about, but this is sort of an entropy regularized version of optimal transport. Sort of people have been quite interested because it's sort of a natural generalization of diffusion models to paired data from a general source to a general target. You can do this sort of slightly altered, right? It still fits in the framework. You have this Q of Z that's the entropy regularized transport matrix, and you have a sigma that sort of is a Brownian bridge. So it's as small at the ends and wide in the middle. So this is sort of marginal OT in the entropy regularized sense, which is quite close. Yes.
I'm
Yeah.
kind of
Sorry.
confused about the difference between OT-CFM and Schrödinger bridge CFM.
Yes, perfect. Yes, so maybe one way to think about it is so entropy regularized transport is this sort of idea that it should be, well, okay, maybe I should start with Schrödinger bridges. Maybe it would be useful. Let's see, I can just flip to there. Schrödinger bridges is kind of interesting problem. Basically, you're looking for the path measure that minimizes the key-out divergence to this reference measure, and it's constrained at both ends. You want your endpoints to be the idea is you observe two distributions, and you want to find the sort of most likely stochastic process that gives rise to these distributions, right? Q in general is just like Brownian motion, something like this, and you want to sort of find the P. So if Q is Brownian motion and P is your sort of process you're trying to find, and as Brownian motion goes to 0, then you recover optimal transport. If this Brownian motion has non-zero standard deviation, then you get this sort of entropy regularized transport. So you sort of get the smoothing out, so that each point sort of moves to each other point with some probability. It sort of walks randomly. And so in particular, there's sort of this mixture transport. So you can look at the sort of this optimal solution P as a mixture of Brownian bridges between the entropy regularized solutions. So basically one is sort of a limit, basically. So optimal transport, you can think about as a limit of entropy regularized transport. Entropy regularized transport is quite interesting because it has sort of better convergence properties and it's easier to calculate than standard optimal transport.
Okay, so can I give it an attempt?
Yes, please.
OT flow matching, the OT conditional flow matching. I don't like calling it conditional flow matching because flow matching is also OT joint conditional flow matching. Then we still end up with the optimal transport. Oh yeah, we end up with the optimal transport from our start distribution to our end distribution. But if we have the Schrödinger bridge, then the marginal of our process is minimal with respect, or the KL divergence of the marginals of our process are minimal to the marginals, to which marginals, to which process? Like some Brownian reference.
Yeah, so Brownian reference, but constrained, right, at both endpoints, right? So, if you only constrain at one endpoint, then you sort of have, you would just, right, like sort of, diffuse over time, basically, right? But if you constrain the other one, then it's sort of like diffusion, but constrained that you also observe time one.
Okay, and now why would this be cool? Like, why do I want, why is the Brownian motion constrained to these endpoints?
So I guess, applications wise, so this sort of diffusion Schrödinger bridges was one of the first papers that looked at this. They sort of do image-to-image translation is one of the ones, right? So unpaired image translation is one of the motivations. I think this doesn't quite work that well yet because like Euclidean distance is bad for images. You can do it basically. And you can also do generation, right? Like just from Gaussian to data. But and so this sort of maybe is better. I don't know. They've shown sometimes
everything that you're saying is
yes.
I can also do this with OT joint CFM, and now we have our Schrödinger bridge CFM where we have this reference path, and the reference path is I mean, it can also be another one. It can be the reference path of OT-CFM. And then we end up with exactly the same as OT-CFM. And then why is now the Brownian one the one that I want?
Yes, yeah. So I mean, so empirically, maybe this is just so okay. So this is just a generation task in different dimensions. So it's from a Gaussian to a Gaussian. So not very interesting, but sort of so Schrödinger bridge CFM is our sort of deterministic one, right? And SF2M and DSBM, these are all sort of the stochastic versions. So these are all, you also learn the score in some sense. So basically, SDEs work better in high dimensions for some reason. We have suspicions why, right? It's sort of like if you have too many dimensions, your OT, your sort of flows are very sort of brittle in a sense, because if you go to some place where you haven't seen before, then you don't know what the flow is there, and the flow may be large and in the wrong direction, right? Whereas sort of this the score is kind of interesting because it always draws back to the data. So even if you don't observe that many data points, oftentimes the score function will just draw you back towards the data anyway, even outside of your domain. So a lot of the times when you don't observe everything in high dimensions, it actually works better to do these stochastic paths. When it's sort of lower dimensions, definitely the sort of deterministic is just easier to learn and is faster to integrate.
What am I getting wrong
Yeah,
here? Why is
sure.
Schrödinger bridge CFM deterministic?
Yeah, that's great. So yes, yes. So all so Schrödinger bridge CFM. Let's see, did I talk about? Yeah, so right, this is a deterministic thing in that it is the same. We use the same procedure, right? We just learn this UT. That is the Schrödinger bridge, but the only difference is basically the conditional and the Brownian and the standard deviation, right? So this, we're still regressing in the same way against this. Sorry, this is the mean, but we're still regressing against a deterministic UT of x given z. But so there's no stochastic, right? So we call this Schrödinger bridge, but it's a Schrödinger bridge marginals, right? It matches the marginals, but it does not match sort of the true Schrödinger bridge, the stochastic Schrödinger bridge, which is close to the Brownian motion, right? Like this is a deterministic flow, but it matches the marginal. So it's sort of like the probability flow version of the Schrödinger bridge.
Okay.
But if you add back in the stochasticity, it works better. Anyway.
But we now never talked about any stochasticity here, right?
Yes.
Up until now, we never had anything stochastic.
Yes.
Or we have a lot of stochastic stuff, but let's say during inference, when we simulate, we never have any stochasticity. So where does your stochasticity come from now?
Yeah, so that's in the other paper, basically. So yes, I don't know if we want to talk about that. I have a few slides if we want to, but yes, that's so yeah, maybe we'll just briefly preview this. So okay, so turns out, right, so there's a couple different ways of thinking about this. Equivalently, there's sort of diffusion Schrödinger bridge matching, and there's another paper, I forget, it's IDBM, but they're basically similar ideas in that you want to do Schrödinger Schrödinger bridges by matching these sort of these Brownian bridges over time. So we regress in a slightly different way, but they're all very, very similar ideas in that you want to sort of add the stochasticity back. So you want to match the stochastic flow. And so what we do is learn sort of the flow matching loss. So the same thing, exactly the same thing, right? This would be equivalent to doing SPCFM, but then we also add this score matching loss. So we match the condition, right? The actual score or the conditional score over time. And so this gives you basically flexibility. And so you can start from any source and go to any target, just using the sort of flow matching and the score matching losses together. These can be two separate networks, right? Or two heads of the same network. But yeah, so this would basically allow you to add stochasticity back in because you now have the sort of ODE flow and you have the score. And so now you can either simulate an SDE or simulate an ODE.
Okay, and then what do I have to do? Do I have to change my conditional flow somehow? Do I have to change my sampling somehow for training? Or do I have to change anything else besides putting in this extra term and training this additional model?
Short answer is no. Longer answer is you probably don't want a flow that has like right, like Dirac, right? So just going back here, right? If your like standard deviation is 0 all the time, then your score is very not interesting, right? Like it's 0 everywhere and then infinity near you. So this is very hard to learn, right? So you want a sort of smoother standard deviation. So something like this, right, works much better with this sort of flow and score matching. Yeah.
Okay, so in your SF2 whatever paper, you don't use a constant
Correct. Yeah, we always use this, exactly. Yeah.
and you find that it's much better.
Yes. Yeah, exactly. So yeah, constant has to be very small because you want it to match, right, the margins both sides. So yeah, basically small score is very numerically unstable, right? Even though mathematically it works fine, it would just be like moving and very very sort of, yeah, you have like lots of, yeah, it's very very annoying. Yes.
Would be also like we're back in diffusion model intuition land.
Exactly.
Okay.
Yes.
Then what else?
Cool. Yeah, let's see. Okay, so I just want to say, right, like, why do you want to do this OT thing? So if you want to do dynamic OT, which is sort of the application that I'm interested in, it works quite well, or at least approximates quite well. If you want to, it sort of reduces the variance in the objective, so it speeds up the training and it reduces the inference time by creating simpler flows. So just some sort of short experiments that show this, right? Low dimensions, so many different models, OT-CFM, and sort of these rectified flow models also sort of are doing OT-like things, but not exactly. And so they do quite, right, like fairly well and sometimes better, but on average they do a little bit worse than OT-CFM. And then that's basically the OT works quite well in low dimensions. OT in high dimensions, right, is quite strange because you're trying to estimate it from samples. So yeah, you might not. It doesn't make much sense to do like Euclidean OT in high dimensions. So we mostly do it in low dimensions, basically. But in higher dimensions, you can sort of use it to reduce variance in the objective, right? So thinking about what I said before, right? Like the variance between the conditional and the marginal flow basically goes down as the batch size increases. And so in fact, it goes to 0, right, as you achieve OT because none of the paths cross, right? So this is sort of minimizing, right? If none of the paths cross, then the variance is 0 and you're sort of always regressing against the same direction, right? And so that's an easier thing to learn. So larger batches, easier to learn. We also try this sort of batch averaging thing. So we average the flows over multiple batches, and then this also seems to help a little bit, but that seems to be worse than just like doing many batches, basically. So yeah, we like, or just increasing your batch size, basically. So basically the best we've done is sort of mini batch OT size is same as the model batch size, but yeah, could do bigger batches potentially. I don't know.
Okay.
Yeah, sorry.
How fair do you find it of me to say that flow matching doesn't yet really generalize the diffusion models, and only now that we have SF2M, we really have generalized diffusion models, because we also want to use SDE integrators during inference, and yeah, now we have everything that we need and really have no reason to train a diffusion model anymore.
Yeah, I mean, I think they're very similar, right? Like would you really call this not a diffusion model, right? Like if you pick the specific flow that had, the flow be 0, right, and just the score, then of course, it's fine.
I mean,
you've actually trained a diffusion model, right? So yes.
Yeah. You're training a diffusion model at the same time, and you could leave the F fixed even. Like you just additionally, maybe a description of your paper here is you train an additional diffusion model, and yeah. But like these methods of flow matching, we don't like it, or I don't like it for generative modeling from some Gaussian, or starting from a Gaussian. I like it because we can now start from arbitrary distributions, and we no longer, now maybe in some case we know we have some prior from which we know, yeah, it's already pretty close to our data, but we wouldn't know how to design a diffusion model to end up with this prior and to then reverse the process. But now we can just say, be like, oh yeah, I have all these molecules or so that already look very similar to the distribution of molecules that I want to generate. And now I can just start from this molecule distribution where the distance, in whatever way you want to see it, is very low to the target distribution.
Yeah, I agree. I think this is quite an interesting application. The image, you sort of get modest, very modest gains, right? Especially in sort of, number of function evaluations, right, is sort of the clearest case. But yeah, it's sort of much less clear than, yes, now I can do something I cannot do before, right? So yes.
Yeah. The image people. Okay.
Cool. Yeah. Okay. So yeah. So we did this on CFAR 10. So these are we tried to match the Lippmann paper, but there is not enough details. So we don't know what exactly they're doing. We don't get quite the performance. So they got a performance of 6 here, right? We got a 9.4. We have gotten much lower, right, by using sort of tricks that they don't mention. So I don't know. We're unclear exactly what tricks to use, basically. But we sort of the lowest we've gotten here is like right 5, basically, which is comparable. Yeah.
Do the Facebook people not put up code for CFM?
Yeah, so they don't have any code for flow matching at all, or CFM.
But what are the code bases out there if one wants to go ahead and implement some joint conditional flow matching?
Yeah, so there's there's our code, right, which is here. That's just conditional flow matching from me. And then so here's the sort of relevant related work. So this one does not have code. Rectified flow is code. Michael has some code, but it's not perfect, right? This one actually has code. So Facebook released Riemannian flow matching with code. Code came out like last week, I think. Action matching has good code. I'm sure you'll hear about that. Diffusion Schrödinger bridge matching has code. This one has code. This one does not have code. So yeah, there's sort of some code, but not a lot of code. Yes.
Yeah, and then maybe like, oh wait, what is your plan now on what to present? So I'm
pretty close. I can summarize. I can talk about single cell stuff if we want, or not. Yes.
Okay, then let's get into some of my. Oh no, go ahead and summarize.
Okay. Sounds good. Yeah, so just summarize, right, you can train these flow models, sort of like diffusion models with this MSE objective, although it's obviously you've mentioned some of the differences, but yeah, it's quite close. And in particular, right, non-Gaussian source distribution is quite useful in many cases where you have a better prior than Gaussian. And so when you use these fast OT solvers from static OT, they give better flows. And so you can sort of approximate this dynamic OT, quite interesting for me. And this lower variance in your objective function and straighter paths gives sort of faster inference. Yeah. So this is sort of biggest things. And of course, just summarizing, right, like we have sort of 2 ideas on this. So this is our original sort of OT-CFM work, and then this was the sort of stochastic version, and sort of trying to explore, what if we just add the additional diffusion model back in, basically. Yeah. So thanks.
Thank you. Very nice. And then for the simulation free Schrödinger bridges, I'll show you SF2M thing. Are there some caveats why we do not actually end up with the Schrödinger bridge, or is there nothing like that?
Yeah, there's definitely caveats, right? So it's of course, our assumption. So these are very hard to solve. If you have continuous things, nobody can do it in closed form unless you have Gaussians, basically. But we rely on the static OT, right? So we do mini-batch OT. So there's definitely an approximation error between mini-batch OT and true OT, right? So that's one of the biggest things. And then of course there's the numerics problems. But yeah, that's the biggest thing. So I didn't talk about it, right? But the sort of comparable works to SF2M is this diffusion Schrödinger bridge matching. And then there's, so somebody mentioned the aligned diffusion Schrödinger bridges in the chat. That's also quite interesting, right? But they also rely on this sort of paired samples. So they assume you have samples, paired samples from the true Schrödinger bridge. And so you just do bridge matching with this sort of, you already know the pairs. And so yeah, you can do this. There's also IDTM, which is equivalent to diffusion Schrödinger bridge matching basically at the same time. These two sort of outer. So yeah, the difference is basically how you do. I didn't mention this, but there's IPF, right? So interproportional fitting is how you solve these sort of entropy regularized transport problems, and the idea is that you have to iterate back and forth because there's no exact solution. In discrete terms, this is sort of matrix vector multiplication, but in sort of the in the continuous time literature, you need to do sort of solving diffusion Schrödinger bridge in each direction. So this is the algorithm. Basically, the notation here is, right, we don't need to know it basically, but this is basically right, use a matching that's given to learn the bridge in one direction, use the matching in the other direction, and learn the bridge in the other direction, right? So you sort of go back and forth between simulating to find pairings and then matching those pairings using the Schrödinger bridge matching ideas, the flow matching ideas, and then go back and forth. So you sort of do iterative on this outer loop of learning your neural network. So each iterative step is learning your neural network instead of sort of doing this matrix vector for the discrete step. So
how intuitively does the finding the pairing work? Right, you say we do our flow matching, so to say, with without any pairing, and then we simulate from one side, and then how do we continue training from there?
Yes, yeah. So the trick is that right, what pairs would you? So you to find a pair, you simulate from one side to the other, and then right, you learn a whole trajectory, but then you just take the endpoints as a pair, right?
Yeah, but then how do you know that if you take these endpoints as a pair, like you have a crappy endpoint on one side?
Yeah, exactly. Yes, you do. Exactly. This is one of the problems, right? So it only works if you iterate to basically infinity, right? So each time you iterate, you'll sort of get a closer and closer to the true bridge. And so it'll be basically the convergence result says this is convex. And, if you solve the diffusion, the bridge matching perfectly every time, then you would sort of get this convergence to the true, to this true Schrödinger bridge.
What if we sort of simulate our, what if we simulate and then we don't use the crappy points, but we kind of use some distance to our true points, and then based on this we define our matching, like the point that has low distance, this one, and blah blah blah, and then we have our matching defined between the true distributions this way, and then we do flow matching.
I think that's sort of the idea, right, for the score and flow matching when you condition on the OT matrix, right? So instead of, right, you could simulate and do OT between the two, right? And you would get a slightly better, right, thing, basically. And so in fact, combining these things help, right? Yeah.
Well, what do you mean? Like here we just do OT. So let me make a very controversial statement about OT flow matching now, or very bad statement about OT flow matching. It is just it doesn't help us solve OT. It basically says if we have solved OT, then we can solve OT for training a Schrödinger bridge.
Yes, that's true.
Yeah, but in this diffusion Schrödinger bridge matching thing, we actually solved the OT problem eventually in a new OT solving way. But now this is different from what you like. What I proposed, that we like simulate, and then we have our new distribution, and we kind of calculate these distances from this new distribution to our our target distribution, this to this, and then based on that we assign, yeah, if this point is close to this one, which we know belongs to this point, then we now use it for conditional flow matching between these two guys. And yeah, maybe one doesn't have to solve the OT problem between this and this. And even if one has to solve the OT problem between this and this might be rather easy, or much easier, because here we only have 10 samples and here we have our data distribution.
I see. But then you're introducing bias with your 10 samples, right?
Yeah, sure.
Okay,
But
yeah.
I am just throwing out some.
Yeah, no. Yeah, I haven't thought about that. We were trying to write like, I think sort of the most effective thing, right, is to start with sort of the mini-batch approximation and then do more iterations, right, using simulation if you need to, right? So this requires simulation. If you do this iterative splitting, you'll eventually get there. So, but starting with a mini-batch thing, it works, fine-ish, right? Even starting with independent matching, right? That's what they do here. You start with an independent one, match for a while, and then go into iterations, right? So even with independent matching, you get quite close, right? Because you still get data points, right? It's not perfect, but yeah, it's yeah, pretty good.
Okay, and then geometry, Riemannian, geodesic flow matching. Can you use a few words?
Yeah, so this is a very cool idea, right? So obviously OT applies to any geometry and flow matching. So what they do is essentially pick a point on the manifold as the starting point, right? Instead of a Gaussian, it's just a point, but then find the flow to that point along the geometry. So it's you can do it for fairly general Riemannian things, sort of depending on which geometry you choose. If it's simple, they call it then. And if you have sort of closed form geodesics, right, then you do the same thing. So if you have a closed form geodesic and you know the flow along that geodesic, then right, you just need the flow in the tangent space. Then you can sort of do a matching on the tangent space at every point. So sample from the flow and so do the same thing. And if you know the true conditional flow between those pairs of points, then you're good to go. Yeah, that's very, very nice. So yeah, you can learn, on Riemannian manifolds just fine. And the same ideas for OT, right, also apply. If you had OT, easy ways to calculate distances on your manifold, then yeah, you can do OT very quickly also. So, yeah.
So are we just saying, yeah, we now can choose whatever path we want? Of course, like this is the whole reason for this work, so to say, or these works. And now we're saying, yeah, good. Also, you can choose every path you want. Choose a good one.
Yeah. So the key is right. Yeah. Sorry.
Now, then this becomes unintuitive for me. This straightness idea. For example, you had your loss with your x0 minus x1 that we're matching, and now, yeah, if we have a curve, so to say, of some geodesic, then how do things change, or could it ever be that I still have such a simple loss formulation in the end?
Yeah, so it won't be quite as simple, right? It's like you'll need, yeah, so this, right, like you'll never have x1 minus x0. That's always the straight line. But of course, it'll be instead just like some ut of x given z. So yeah, you'll need to know the conditional flow, and it might be changing directions over time for a curve, right? But it's still very simple to give.
Okay. Then what else did I want to say? Right. Let's have a very 5 minutes of cell stuff, like, or application stuff. What are the actual applications that you think are where this can be interesting, apart from geodesics, apart from Riemannian, and apart from cell stuff? Do you have other ideas?
I mean, so yeah, so we're interested in sort of, yeah, I don't know. I'm sort of very focused on the cell things. We were thinking about control things and language model things, but yeah, we haven't fully, right? Like anytime you need one of these diffusion models or CNFs, you could try it, especially if you have a better prior, basically, right? So wherever you have a good prior, then you should maybe think about trying it. But yeah.
Maybe one can train a flow model to go from some AlphaFold proteins to the distribution of actual proteins or something. Yeah. Anyway.
Yes, that would be exactly a good prior for sure. Yes.
Then let's talk the 5-minute cell stuff. Why is this interesting here? Or what do you need, right? We have some problems where we absolutely don't care about having a Schrödinger bridge. We have some problems where we don't care about straightness of, well, that's we basically always care about because we want to integrate faster. But we have sometimes we don't care about a Schrödinger bridge. Now, for your cell problems, what is your cell problem and what is it that you would want if you could have whatever you wish for, if you could have the Schrödinger bridge? Would you want the Schrödinger bridge or something smaller fine as well? Yeah.
Yeah, for sure. That's a great question. So, I mean, the short answer is I don't really know what I want, right? Like I know the data that I want to match, but I don't really know the model that's going to do best at it. We don't, have infinite data, so I can't just split it all up and try thousands of models and see. So, hopefully we'll get there, but currently it's sort of very prior driven. So using, sort of priors about what we know about cells to do better inference. So basic idea of the task. So we have a bunch of distributions of single cells over time. So each cell is represented as sort of a histogram over its RNA. So its RNA is sort of the sort of state of a cell. So you can think about a cell as sort of a vector in 10,000 dimensions, say, that represents like what it's doing at the time. And so you want to say like, here's a developmental process, or here's a disease trajectory of cells. And the idea is sort of link up the cells over time and to see how individual cells over time, right? So the problem with this collection method is that it destroys all the cells because to sort of read them out, you need to explode them and read all the RNA. So you never get matching. So you want to figure out what a cell is doing sort of over time and trying to figure out, right, like what makes a cell go one way versus the other, sort of what would happen if you changed a cell, right? So what happens if you apply a drug, for instance, right? What, which way would it go, right? And so this is the general idea. And so we're doing this sort of in the lab also, but there's sort of many different ways you could try and infer this thing. And so our current task is basically to take all the time points, leave out one, and then do some sort of trajectory inference, right? Sort of, OT-CFM, for instance, right, over time, and see how well the true distribution matches the predicted distribution. And that's sort of a crude, right, supervision in that it's sort of distribution wise, but it's sort of one of the, at least it is a true measure rather than a, yes, there's many other ways to think about it, but yes, there's a sort of clustering based, anyway, many different evaluations, but this one is sort of like, yes, this is how you would match the data. If you had infinite data, this would work perfectly. So, well, maybe not, we need infinite time and space, but anyway, yes. So this is the idea, and so yeah, we've been testing this sort of model. So we need, in these cells, right? We need stochasticity because we know, well, at least to our knowledge, right? Cells, the same cell could go to different places depending on sort of external factors that we can't measure, and whether and then we need like sort of manifold ideas and unbalanced transport ideas, so cells can grow and die, right? There's many sort of different ideas that you need to incorporate to model these cells over time, and I don't think we have a nearly accurate model yet, but it's hopefully still getting insights out of them. So the idea is, right, basically to learn this vector field and then to interrogate the vector field and see where cells might go if you apply to perturbation.
And then do you have a reason, like, do we want to train a Schrödinger bridge here or not?
Yeah, so I know there should be stochasticity, right? So the many of the sort of stem cell populations, which is the origin cells, are very similar to each other. and I know that there's sort of no information about where they go. So I do need a sort of something where the conditional paths match up what I expect. So we have some sort of lineage tracing information that says this population of cells goes to this one and this population goes to the other, right? Or this population goes to both. And so to sort of learn this population goes to both, right? You need some model with stochasticity. And whether, of course, that's Gaussian is a whole nother matter, right? But that's sort of better than sort of ODEs, right? So
because one could imagine, or it sounds to me much more of a plausible model, so to say, that we have a energy landscape underlying this, that is where if we move around, it is not Brownian motion in this.
yes.
Yeah, it is not
Yeah,
Brownian.
so
In addition, we have some energy landscape, and we want we want our path measure or KL divergence between path measures to be minimal to that the paths given rise to by this energy landscape. Oh my, this is
yes. Yes, that's very interesting. Yeah, so sort of at the lowest level, we don't think they evolve according to energies, because that basically, if your velocity is a gradient of an energy function, then right the derivatives are symmetric. So that would mean that like each gene causes if one gene causes the other, then the causality goes both ways, which is just not how genes work in practice, right? Like some genes affect others. So, but of course, at some level, right, it is an energy landscape, right? So we think about it, and it's quite a useful abstraction. So there is an energy landscape between states, just how exactly to represent it. So we are trying this, right? But it's not, we don't know exactly how to apply it in terms of this causality stuff yet too. But yeah, sort of the action matching approach, right, is the vector field is the gradient of an energy function. And that's quite useful. So all the flows I've been talking about, right, can be represented as the gradient of energy function, and you can do sort of interesting loss functions based on that. So yeah, it's quite interesting too. Cool.
Yeah, a big thanks from me to Alex for all these presentations, for making conditional flow matching much more clearer to me, and hopefully also to all the audience. And if you want to take advantage of awesome people like Alex in the future and understand a particular paper yourself better, then suggest them. In the description, you will find a link to our Slack channel where you can chat to me, for example, and write me a paper that you would like to see in the reading group. Otherwise, it will just always be the papers that I'm the most interested in, and we will have exciting discussions about them in the future, like next week. So see you next week, friends of the sun.